Welcome. This video is going to look at some more of the problems from Section 3 in Chapter 1 of the Brown SL Chemistry book. Starting with 45, we start getting into the gas laws, and 45 is working with Avogadro's concept or discovery that at STP, 1 mole of any gas will be 22.7 decimeters cubed, or what we commonly think of as a liter. Now, to finish 45, you're also going to have to remember that there are 10 decimeters, or 10 centimeters in a decimeter, and 10 decimeters in a meter. So for A, we're given 54.5 decimeters cubed. So this one is pretty easy to carry out. I could just divide by the 22.7 liters or decimeters cubed. I guess I should stick with the decimeters cubed since that's what IB uses. And so 54.5, this will be around 2, I'm guessing. 22.7, 2.40 moles for part A. For part B then, I've got 250 centimeters cubed, so before I can use Avogadro's constant, I need to change to 250 centimeters cubed. Well, if there are 10 centimeters in 1 decimeter, I need to cube this. Well, 1 cubed is still just 1, but this can become 10 to the third, so I really am dealing with 0.2500 decimeters cubed. And now when I take 1 mole over the 22.7 decimeters cubed, this is just 0.25 divided by 22.7, 0.011, and if I hang on to my sig fig, 0.1101 moles of gas. And you notice I didn't even include what kind of gas each of these were, even though the original problem did, because it really doesn't matter. That's the whole point of Avogadro's principle. And now with my 1 meter of gas, I have to convert that to decimeters, and I see there's 10 decimeters in a meter, but again, I have to cube both of these, so that means that also becomes cubed. And so this is going to be 1,000 decimeters cubed divided by our constant 22.7. And we're looking at 44, since I only have 2 sig figs, moles of gas. On number 46, in part A, they give you 44 grams of N2. Both these gases are at STP, but I need to know my molar amount, so if I divide by the 28.02 grams in a mole of nitrogen, this is actually 1.57 moles at STP times the 22.7 decimeters cubed I would expect in a mole, gives me a volume of 35.64. Decimeters cubed. Part B, it's in moles, 0.25 moles, so it really doesn't matter what kind of gas it is, because I know that any gas at STP is going to occupy 22.7 moles per liter, or liters per mole. So times the 0.25 moles, so 5.7, going with my sig figs here, decimeters cubed of gas. So as you read through 47, here's the information they give you. They give you a balanced equation and tell you have 12.45 of mercury oxide. And you want to know how many decimeters cubed of oxygen gas that should produce at STP. So again, I need to find my molar amount of HGO so I can determine my molar amount of O2. So 12.45 grams, if I divide by the molar mass of 216.59 grams, I'm getting a molar amount of 0.05748 moles of the reactant. And I see it's in a 1:2 ratio with O2. I only get 1 O2 from every 2 moles of HGO. So my molar amount of oxygen is just 0.02874. And now it really doesn't matter if it's oxygen or any other gas, because at STP, I can expect it to occupy 22.7 decimeters cubed per mole. So I can expect 0.65, how many sig figs do I have here? 6524 liters of O2. Number 48 asks, which of these contains more particles? More molecules specifically. So 3.14 decimeters cubed of bromine or 11.07 grams of chlorine. Now they say at the same temperature and pressure, so that means as long as I use the same conditions for both, I can choose them. So I'm going to choose STP because that means I can easily come up with the molar amount, which I've got going backwards here. I know that 1 mole would occupy 22.7 decimeters cubed at STP. So that means my 3.14 decimeters cubed is only 0.138 moles of Br2. And moles is an amount, so whichever one has the greater molar amount is going to have the greater amount of molecules. So now my Cl2, I can go ahead and change that to moles because I know 1 mole of Cl2 has a mass of 70.9 grams. So even though this is a gas, there's no need to check out the volume because I've got the mass. So mass and volume is just the way to get to the molar amount, which is how we do all of our comparing in chemistry. So I put 0.156 moles of chlorine, which means chlorine would have the greater number of particles. So in question 49, they want to know the volume of gas produced when 0.200 grams of calcium reacts completely with water. So they're letting you know that calcium is the limiting reactant. That makes life a little easier. And they say how much gas. There is only one gas in this equation, so really they're asking for the liters or the volume of hydrogen. So 0.200 grams of calcium, if I convert that to moles, 40.08 means I have just 0.00499 moles of calcium. And I see it's in a 1-to-1 ratio. I just noticed I didn't have that balance there. But it's in a 1-to-1 ratio, the moles of H2 and the moles of calcium. So I know I have 0.00499 moles of H2, and I've been told it's at STP. So I can expect 22.7 decimeters cubed per mole. And if you prefer to write liter, IB won't dock you for that. They realize that's what it means. They're interchangeable. But I could expect 0.113 decimeters cubed of gas, which would be hydrogen. So number 50 is similar to 49. I have a gram of reactant that's going to decompose and produce this gas, and I want to know how much gas I'm going to get. So I need to know my moles of reactant, so I can find my moles of gas and then find my volume. Since this is happening at STP, I can just use Avogadro's constant. So 1 gram, I need to go ahead and divide by the molar mass of 80.06. So we're dealing with 0.01249 moles of reactant, and they're in a 1-to-1 ratio. So this is how much N2O I'm going to produce as well, 0.01249. So that means I can go ahead and multiply by the 22.7 decimeters cubed that are found in any mole of gas. And I should expect 0.2835, although I've just got 2 sig figs here, so 0.28 decimeters cubed of N2O.